For this lesson, we're going to be going over permittivity and the associated terms with it. That would be electric field intensity, electric flux density, and electric flux. And we're going to go over some practice problems to get our feet wet with those particular terms. The first associated term we'll go over is electric field intensity, which has a symbol of a capital E. Electric field intensity is the area in which a potential difference between two surfaces creating a field of attraction. Now, in the majority of our practice problems, we're going to use two parallel plates just to keep it simple, but associate it with a capacitor. It has two plates, and we're trying to find the electric field between them. And this electric field is measured in volts per meter. Now, be aware, you might see this on a test or practice problem. Electric field intensity is also called electric field strength. They mean the exact same thing. So be aware of that when you're doing your practice problems or you see it on an exam somewhere. Our next associated term is electric flux density, which is symbolized by a capital D. Electric flux density is a measure of electric field in terms of equivalent charge per unit area. So think of it like this. In a rainstorm, every raindrop is electric flux. And if you have a high amount of raindrops in a little area, you have a very dense rainstorm, which is your electric flux density. Now, if you want to take this metaphor a step further, in a very thick rainstorm, you might see a bunch of lightning, which in a sense is correlated to electric field intensity. So electric field intensity is proportionate to electric flux density. And we're going to go over this in a few more in the practice problems. Be aware, electric flux density can also be referred to as vector flux density. So if you see that on a practice problem or on an exam, they mean the exact same thing. Now the meat and potatoes for this lesson, permittivity. What is permittivity? It's the basic property of the dielectric medium, also known as the dielectric constant. So what does this mean to you? Well, if you look at the illustration below, I have two conductive plates with a blue area in between them. Well, that blue area is your median. Your blue area could be just free air, plastic, wood, even rock. It all depends what they have for that particular problem. Be aware, you must multiply your free space constant times your relative permittivity to find your total permittivity. And we'll go over that more in the lesson. Now, also something you need to be aware of, some of your books may have the relative permittivity like tables and some of your constants. However, if you look between some of your reference material, all those numbers may not be consistent. If you look up wood, it may be different from one book to another slightly. So be aware, on some of your practice problems, usually relative permittivity is given. But just so you know, relative permittivity for air is 1, so free space and air are going to be the same thing. And we'll go over that more in a practice problem. For this last slide, just to minimize confusion, I want to go over permittivity versus permeability. One of our previous lessons, we went over permeability, which had to do with magnetic fields, magnetic flux, and strength and intensities. Whereas this lesson, we went over electric field strength, electric flux intensity, and electric flux. However, there is some major key difference between the two. When you think of permeability, think of magnetic fields, think of inductors. When you think of permittivity, think of electric fields and capacitors. That'd be the best way to kind of determine between the two and kind of set your mind apart and not get them confused. So just be aware that there is a difference between the two and the associated components with them. So let's go ahead and jump into some example problems. Alright, so let's jump right in with a practice problem. The voltage between two parallel plates separated by a distance of 0.01 meters is 300 volts. Determine the electric field intensity and the electric flux density. The dielectric is air. Alright, so we have a few variables to work with. I think we can knock this out. Well, let's log what we know first. So right now we know distance, so we know delta, which is 0.01 meters. So that's pretty simple. Next we know voltage, which is 300 volts. And we want to find the electric field intensity, so we want to know what E is. And we also want to find out the electric flux density, which is uppercase delta. And let's see if I can draw a diagram here to give you an idea of what we're looking for. So we have a distance between here and here of 0.01 meters. And then we have a voltage of 300 volts. So this provides you a diagram we're looking for with two plates. To find electric field intensity, it's going to be E equals V over distance, or voltage over distance. So that one's pretty simple. So it's going to be intensity or strength equals 300 volts over 0.01 meters. And that's going to give us a final answer of, put it in our calculator, it's going to be approximately 30,000 volts per meter. Okay, so that'd be our answer for A. Now for B, the electric field density, which is D. So to find the density, it's going to be the strength or intensity times the dielectric. Since the dielectric is air, it's going to be the relative permittivity times free space, and that's going to give your actual permittivity. So it's going to be, and which means our relative permittivity for air is 1. So it's going to be 1 times the free space. And free space equals, just so we have it in front of us, it's going to be 8.842 times 10 to the negative 12. And times 1 gives us, obviously, 8.842 times 10 to the negative 12. So to find our density, it's going to be our permittivity times our intensity. So D equals 30,000 volts per meter times 8.842 times 10 to the negative 12. Okay, that's farads per meter. So give us a final answer of D equals 2.652 times 10 to the negative 7. That's coulombs per meter square. So that would be B. Alright, let's try another problem. For this one, we're going to mix it up a little bit. The electric field intensity between two parallel plates is approximately 20,000 volts per meter and has an area of 100 centimeters square. The dielectric is polyethylene, which means the permittivity is 2.26 according to our PE reference books and all of our material that we have. For this one, we're going to find the electric flux. Not the intensity, not the density, just the electric flux. Alright, so we're going to jump around by, see if we can show you the model real quick. And of course, we're going to log what we know. So we have E equals 20,000 volts per meter. We have an area, which is A, of 100 centimeters square. Now before we move on, we need to go ahead and convert this 100 centimeters square to meters square, because everything we're doing is in meters. So we're going to have to convert this down. 1 centimeter equals 0.01 meters. Okay, simple fact, nothing difficult. So which means 1 centimeter square equals 0.01 meters times 0.01 meters. Make sense? And that's going to come out to be 0.0001 meters square. Okay? However, for this one, we have 100 centimeters square. 100 centimeters square is going to equal 100 times that, which is 0.01 meters square. And that'll be the variable we use, because all of our calculations are in meters, so we're going to have to keep it in that particular unit. So that would be the guy we use. Be aware of this. You might actually see this on a problem somewhere along the line, either your practice problems or anywhere else. You got to make sure you can convert centimeters, millimeters to meters when needed. So be aware, we're looking for flux. That's what we're looking for. To find flux, we can do density times area, or area times intensity times the permittivity. Well, I think we can find permittivity because we already have the relative permittivity. We have the intensity or strength, and we now have the area. So that's pretty simple. So let's see if I can make room right here. Flux is going to equal area, which is 0.01 meters square, times 20,000 volts per meter. Now here's the issue. We need to find the permittivity. Well, to find that, it's going to be free space times the relative. Well, so right there, I'm going to keep that as E just so we have a placeholder. I'll tell you what, let me clean up some space real quick. There we go. Maybe room off to the side here. So permittivity equals free space, which is 0.842 times 10 to the negative 12 times the relative permittivity, which is 2.26. Make it easier to see. So that's going to give us a total permittivity of, it's going to be 1.998 times 10 negative 11. And I'll tell you what, just to keep it simple on us, because this is very relative, let's make it 2.0 times 10 to the negative 11. Okay, so we have right there our permittivity, which we can put over here, which is 2 times 10 to the negative 11. So we plug and chug this in our calculator. It's going to give us a final answer of 4 times 10 to the negative 9 coulombs. And that right there is going to be our final answer. Hopefully this is enough information to make you dangerous. And I hope you all have a good day.